Okay, what you could see in there is the first slide on the definite integral. You should be able to know how to evaluate definite integral. That way, you will be able to come up with the numerical values of the unknowns in a particular problem. A problem that can be best modeled, mathematically modeled using integral calculus. So we're now on the first set of slides for enter, and that's the definite integral. This will be also shared in your Canvas after the class ends. So as for the learning objective for this topic, you are expected to be able to evaluate definite integrals. And since this is already a definite integral, your answers will not be any more functions of any variable, but rather it would be a real quantity, a real number. Now, if we're going to review on the concept of integration as a process of anti-differentiation, you see these examples here on the left. They are functions of x, and you have here y on the last part being equal to 4 sine of 2x. If you differentiate these expressions that you have on the left, you will get the derivative on the right side. And as such, you could see that the f of x here is written as f prime of x, meaning it's the derivative already, and you take the derivative of x cubed, which is 3x squared. If you integrate this derivative, you go back to the original function that was differentiated. So that is why we say that integration is anti-differentiation. You do the reverse of differentiation. The same principle applies to the next two functions. So you have here f of x equal to x to the fourth minus 2x plus 3, which when differentiated yields f prime of x equal to 4x cubed minus 2. 4x cubed minus 2 in the sense that you use power rule here, and in here you simply took the constant minus 2 because you only have x as the variable. Again, if you're going to integrate this using power rule for the 4x cubed and the minus 2, it will go back to this one. But if you notice, class, if the integration process that you did here and the first two functions of x prime here, especially in the second example, it will not give you a specific constant, which is 3. If 4x cubed minus 2 is integrated, it will only give you the first two terms. Why? Because if you integrate this as an indefinite integral, it does not have limits, you add here a plus c. That c, that arbitrary constant that appears when this 4x cubed minus 2 is integrated, will account for or will be the representation of the specific constant plus 3 that you see here. Anyway, that will be elaborated as an example in the next slide. Now, for y equal to 4 sine 2x, you need to differentiate it. For example, you get dy dx because you differentiated y in terms of x, so dy dx equal to, you have to use chain rule here. Chain rule in the sense that your sine of 2x will have a derivative of cosine 2x to dx, or times 2. So that is why you have here 8. Because you need to differentiate as well the argument of the sine, which is 2x. Now, if this is integrated, it will go back to this one. Okay, that's showing you that your integration is the opposite of differentiation. But let's move on. Now, let's say, for example, these particular functions here again, if you're going to differentiate, this one is x squared plus 5. The second one is x squared plus 3. And the third one is x squared minus 7.5. If you're going to differentiate this, they all have the same derivatives. Because of the x squared here, the x squared here, and the x squared here. And because of the fact that the derivative of a constant is 0. And notice that if you're going to integrate here, the answer, the derivatives, it will go back to the original. But again, you won't have the constants. It's because instead of the constants here, you will have plus c. Okay? Now, it's not weird in that sense because when you integrate, you have plus c. What is weird is this. They all have the same derivatives because the same variable is presented on the first term and you have constant added or subtracted from that. Okay? Now, in integral calculus class, specifically definite integral, when you evaluate this, there won't be any ambiguity anymore. So when I speak of ambiguity, not clear. Because the definite integral now does not have the presence of the c, but it specifies what is that c, depending on the limits of the given integral. So let me proceed. So the manner that you need to specify the constant in a particular integral will be taken care of when we talk of the definite integral. If you're integrating only 2x, you have simply x squared as the answer plus this arbitrary constant. And this arbitrary constant is enough to represent the 5, the 3, and the negative 7.5 constants in all three examples that were differentiated. Okay, now we proceed. Now you have this, and you have the plus c when integrated. You have this, when integrated, you have the plus c. You have this, when integrated, you have the plus c. So the reason why you don't see the constants in the original function, it's because you have the plus c when you process an indefinite integral, an integral without the limits. Now let's go to the definite integral. So according to Leibniz, okay, this is how we represent a definite integral. Nothing so difficult about the representation. The only difference of this representation with the indefinite is the presence of the limits. In here, the limits are a to b. A is said to be the lower limit. B is said to be the upper limit. In some statements, these limits are referred to as the interval to which the function is to be integrated. So you may encounter the word interval limits. They all mean the same thing. Okay? Now, you may wonder, what is this limit thing here? When you are evaluating, or rather, if you are processing a definite integral, the one that you have in here on the rightmost part that is shaded yellow, it's like getting the summation of the function of x delta x area. Now, one of the many applications of integral calculus is determining the area under the curve of the function that is given in the integral. What do I mean by that? If this function of x, is plotted on the xy plane, and if its area is determined from x equal to a to x equal to b, that would be the same as taking the limit starting from k equal to 1 to n of that particular area when it is divided by n times. What we do, class, with the area under the curve is we divide it into several pieces of rectangles. We divide it into rectangular pieces and then add those areas of rectangular pieces, and that would be the area of the curve under it. That's what we do. But of course, we don't do that. It's just a, shall I say, metaphorically speaking, comparing the procedure of integrating and finding the area. It's just like that. Kung sa aton pa language, nga para maintindihan nyo, kung na-plot nyo na ang curve, pag gusto nyo i-determine ang area under sa curve, sa sininga limits nga A to B, do pari, wala na nga gin-divide mo na ang area sang ina nga region to n times. Pag gusto ka lang. The more the n, the more accurate is your area. And the individual areas that you have, that is the result of your division, will be summed up, and that would be the area under the curve. But that would be explained later. So I'm just explaining it here now because when you take the value of a definite integral, or when you evaluate a definite integral, it's just like taking a summation of the product of f of x and delta x as n approaches infinity, whatever is this n is, the number of divisions that you have made in the area under the function. That's how it is to be interpreted when you speak of the definite integral as an area under the curve. Now, so when you speak of the indefinite integral, you have the presence of the arbitrary constant in the answer. In the definite integral, you don't have anymore the plus c, but rather when evaluated, it will yield a numerical or definite value. So no function answer anymore. The only real difference between the indefinite and the definite integral is that there will be limits on the integral sign. And that's the upper limit and the lower limit that I'll be showing in here. So this is your definite integral. Your x squared, when integrated this time, will be integrated from 2 to 4. So this is the lower limit and this is the upper limit. And this makes it a definite integral. Now, for example, if you're going to evaluate that particular function x squared from 3 to 6, you just evaluate this based on the tools that were taught to you. You choose the appropriate tool, and that would be your power rule. So if you use power rule here, that will be x cubed over 3, starting from 3 to 6. What you do, you substitute first the 6 as the upper limit to the x, the constant you copy. So that's the reason why you see this. When x is equal to 6, you have here 6 cubed. I'll project this probably so it will be bigger. Okay, this is x cubed over 3, and that would be 216 over 3, giving you a 72. That is if you substituted the upper limit. If you substitute the lower limit to the x, you will have 3 cubed over 3, and that would be 27 over 3, equal to 9. Now, what do you do with these values that you got after you have substituted the limits to the variables in your answer? You subtract these two. The lower limit answer is subtracted from the upper limit answer. So for this definite integral, your answer is 63. So it's not anymore an expression, but rather it is a real value, a quantity. Okay? So that's how simple a definite integral is when you know how to integrate already. So another one in here, that to project, that way it would appear bigger. You're given 6x squared minus x plus 1. You're going to integrate this based on the properties. You are to integrate piece by piece. So this would be 6x cubed over 3. So that would give you 2x cubed. This becomes x squared over 2, and this becomes x. You are not yet done because you still haven't substituted the limits 2 to 5. Now, when you substitute the limits, so you have 2 times 5 raised to 3 for this, minus 5 squared over 2 plus 5. Your answer for that is 242 and a half. If it's the lower limit 2 that you will substitute, you will have 2 times 2 raised to 3 minus 2 squared over 2 plus 2. That would be 16. What happens is you subtract 16, the answer from your lower limit, from 272 and a half. So your answer is 226 and a half. Yes, Mr. Oxenio.
Miss, may I ask if the same na miss, if 242.5, miss? Or, okay.
It's okay. You
Thank
can
you, miss.
answer in decimal. Okay, so this is your answer, 226.5. So the key here is that you know how to integrate, because you will substitute the limits to your answer. If your answer is wrong, then of course it follows that everything that you will be doing after that procedure will be wrong. Okay, now we go to the properties of the definite integrals. It's important that you know the different properties, and I'd like to make this as simple as possible. Okay, I'll project now. Now, in property number 1, we have the existence property. So, if f is continuous on the closed interval a, b, this interval actually, class, is also the limits of your integration, a being the lower limit and b the upper limit, then f, your function, is integrable there. Now, what does this mean? If you're going to plot the function and its curve bounded by points a and b is continuous, then if you're going to integrate that expression, the answer will be existing, meaning you will have an answer to that particular integral. The requirement is for your integral to be continuous. So meaning if the integral is not continuous, or rather if the graph of the function, not the integral, if the graph of the function on the interval AB is not continuous, what do you mean? Wala sang utod ang imo graph sang function on the interval A to B, then the integral of such a function exists. If it has a discontinuity, of course, there won't be any answer to the integral that you evaluate. So that's the number 1 requirement. It's a different thing, class, when we talk about improper integrals, the topic after this particular set of slides. Okay? But for an integral, not an improper integral, the usual integral that we are processing or evaluating, if the curve of the function does not have any discontinuity on the designated limit or interval, then the integral of that particular function exists. If it has a discontinuity, the integral does not exist. Now, we go to property number 2. Now, if the integral of c dx from a to b is evaluated, your answer will be cx, and you have limits a to b, and then you substitute the upper limit and the lower limit to x, and it would look something like this. So the answer to the original integral is c times the quantity b minus a. If c is equal to 1, if this constant is equal to 1, automatically your integral becomes dx integrated from a to b. And that would simply be the difference now of b and a, or specifically we say b minus a, because the c is equal to 1, the c that we have here. So what you have left is just b minus a. If c is 0, then the integral of this expression c dx integrated from a to b would also be 0. This is very important, especially when the integral of any expression is multiplied to 0, class. Anything, including an integral or a derivative multiplied to 0, will be 0. So that's the reason why you have here the integral of dx from a to b when c is equal to 0 is 0. Because you're multiplying the difference here of b and a, or you're multiplying b minus a to 0. Okay? You have any questions? Now, if in AB, the integral of the function evaluated from a to b exists, then we can say that the integral of that same function from b to a is the negative of the original. So what happens here, class, is that you interchange the lower limit and the upper limit of integration. So whenever you interchange the lower limit, just like in this case here, and the upper limit, the value of this is the negative of this one, the original, because you have interchanged the limits. The same thing is true when you evaluate any definite integral. If the limits are switched, lower limit becoming the upper limit, and upper limit becoming the lower limit, as long as the function is the same, your answer from the original will be multiplied by -1. Or your answer now will be the negative of the original. This happens when we interchange the limits of integration. Now, if the integral of, let's say, a function of x from a to b is negative, hence, if you used to find the area of the region below a curve of a function, then the area is equal to the absolute representation of that function integrated from a to b. What does this mean, class? Later on, when we talk about the application of the definite integral, especially when we speak of areas, and the area that you were able to compute is negative, it is only telling you something, that the area that is being considered is below the x-axis, or that is below the curve. You will know that. But if the problem is just asking simply for the area, we are not concerned anymore with the sign. So you're going only to give the absolute value of the area. Okay? If you're asked, determine the area of this, blah, 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 you don't answer negative, because when you speak of area, there is no such thing as negative area. It has only been negative probably because of its orientation. Probably ara siya sa dalom sa x-axis, so negative na siya. Pero kung area lang yun niya, dapat positive na siya. However, you have to take note of this. If you obtain a negative value for an area, don't just take the absolute value of such a number. When you take the absolute value of such a number, be sure that you understood why it's negative. And it will be made plain to you when we reach that particular subject matter. Okay? There will be areas that is negative. And simply making it positive without understanding why it's negative, why you're getting a negative answer, of course, will be incomplete. So you have to understand why it's negative. And it will be discussed. Note, if you obtain a negative value for the area, don't just take the absolute value. Again, so a reiteration. Okay? Now, we'll continue with the properties here. We still have the last 6 properties we have, because we have 10. Okay. If f is continuous on a closed interval, I'll just have this erased. If f is continuous on the closed interval AB, and if C is in between AB, so we say C is greater than A, but less than B, then f is integrable on AC and CB, and we can write it in this form. The integral of the function from A to B is also equal to the sum of these two integrals, wherein this time you made use of C, a value that is maybe in between A and B, not really in the middle, but in between A and B. So you say the function of x integrated from A to C plus the function of x integrated from C to B. If you notice, class, you made use of the C in here. I'll just use the red one. And the one that you have here is upper limit. The one that you have here is lower limit. If you take this out, it's just like you're integrating the same function, f of x, integrated from A to B. So this tells you that, for example, you are to get the integral of, this is just an example, x squared dx from 1 to 10, example. This could also be equal to the integral of x squared dx from 1 to 5 plus from 5 to 10, x squared dx. The 5 here is the c. But it could be any number. It could be x squared from 1 to 3 plus the integral of the same function x squared from 3 to 10. So it's just like you take that out. You're still integrating the same function. As long as the number that you're using here is in between the interval a, b. In this case, our a, b, the example I wrote is 1 and 10 respectively. Okay, I hope you get that. So we can have the integral of something as a sum of two different integrals bounded by the same closed interval. So the integral of a function multiplied to k from a to b, where k is a constant, is equal to, you have to write the constant before the integral, and that would be from a to b, and the same function you write after the integral sign. So this tells you that whatever constant is multiplied to your function, you can write that constant before you integral and then process the integral of the function itself. Whatever is your answer here, your final answer, you need to multiply it by that constant you have set aside in the beginning. Okay? Now, 7 is just an extension of this. If you have several terms, or if you have several functions in which you need to evaluate the integral of, and by the way, class, this is a typo. There's no f of x here because these two are being added. So you're getting the sum or the integral of the sum of these functions. It's just like taking individually the integrals of this function. So first get the integral of the function of x. You add that to the integral of the g of x. So if you have several functions, if you have several terms in your integral, you can evaluate it piece by piece. That way, you will not have one very long function, just one integral. But sometimes, class, others would like to do that because they don't want to write it in this manner, in which for all the terms, you will have to write the integral symbol. If you can process it in just one long equation without having to write the integral symbol for each of the terms, the better. But if you think that it would aid in your understanding that for each terms you write this, then be it. Okay? Because anyway, that's how it should be properly done actually. That's how it should be rather properly interpreted, not done. Because if you're going to ask me if I'm in your shoes, I will not do this because it will only add things to be written in my solution. I'd rather have one long line there and then I'll just evaluate the terms separately without having to write the integral symbol. Okay? Now 8. If f is integrable on the interval AB and f is greater or equal to 0, there then is this particular integral value which is greater than 0. So if this function that you have is integrated and this function has a value which is greater than 0, then expect that the integral value of such a function will also be greater than 0. Because in the first place, its value is greater than 0. Okay, by the way, class, it should not be here equal because if the function has a value of 0 when it is integrated, it will also be 0. So it should only be if the function is greater than 0 there, then the integral of the function evaluated from a to b will also be greater than 0. Now we go to the second to the last. If f and g are integrable on the interval AB, and for every x in AB, f of x is less than g of x or equal to g of x, then we say that if you're going to integrate the function of x from a to b, that would also be less than or equal to the integral of g of x integrated from a to b. Simply put, if these two functions have this relationship, when they are integrated, that same relationship is preserved. So if f of x is less than g of x, their integrals will also be following the same relationship. Integral of f of x will be less than g of x, as long as you integrated both expressions on the same set interval. Not that iniya AB, dasun iniya AZ, hindi naman na siya pwede. So everything being the same, the only thing that is different is that the functions are not equal, are not greater than each other, so less than or equal to, then their integral values will be following the same relationship. Now, the last one is under the application of the mean value theorem, the MVT. So, if your function is continuous on the closed interval AB, then there exists a number C in AB, meaning this number C is in the interval AB, anywhere there in the middle or in between AB, not middle but in between AB, such that the function multiplied to b minus a will be equivalent to the integral of such a function evaluated from a to b. As long as this c, so for example, your AB, like to place a specific example, let's say your AB is 1 and 12 example. And then of course, let's say your C is equal to 7. So this would be correct if we say that the f of 7, meaning you substitute 7 to the variables present in your function here, multiply it to this one, b minus a, so you have 12 minus 1, ay hindi na ako kasulat, 12 minus 1, then that would be equal to the integral of the function of x dx integrated from 1 to 12. That's the mean value theorem. As long as the number so chosen is lying between 1 and 12, or it's within the interval 1 to 12. So you can have this relationship. Okay? That relationship is, I write it here since it's clear, f of 7 times 12 minus 1 is equal to the integral from 1 to 12 of the function of x dx. Okay? These 10 properties, you remember when we talk about the definite integral. If there's a need for you to go back to them and apply them in any situation, then you may do so. Do you have any questions? Okay, so if there aren't any questions, my time here is 3:59. We will have a 5-minute break before we go to the next set of slides because we're going to end by 4:30. Okay, I'll just stop sharing here and then pause the recording. Okay. Improper integrals. The properties that were discussed to you minutes ago will mostly be applicable to the usual integral. These are, shall I say, an exception because they are said to be improper. They're not proper integrals. So what are the learning objectives? So at the end of the topic, you should be able to evaluate definite integrals where the limit is infinite. So there are two classes of improper integral. One is where your limit is infinite, and the other one is when the function has an infinite discontinuity. Now, I will first discuss the first part wherein the improper integral has a limit which is infinite or has limits which are infinite. And then the second part we'll discuss next meeting, or probably I won't be able to cover totally the first part. And then in the process of determining the values of these improper integrals, we should know to distinguish whether it is a convergent or a divergent integral. So the term convergent and divergent integral is actually associated with improper integrals. So while we are doing while we are doing the evaluation of improper integrals, we will determine whether they are convergent or divergent. Okay, so let me proceed to the next part. In defining a definite integral, the function of x dx from a to b, we dealt with the function f defined on a finite interval a and b. When we speak class of finite, defined with siya specific in the interval like 0 to 10, 1 to 5, negative 6 to 10, something like that. So, means not finite. And we assume that f does not have infinite discontinuity. If you recall with the properties of integrals that I have discussed a few minutes ago, number one in the property is that the integral value will exist or may value gid ang integral for that definite integral if the function when plotted on the designated interval will not have any discontinuity. Okay, that's an assumption. Now that's a different story when we speak of these integrals that we're going to tackle for now. Okay, so the usual integral is where the function is defined on the limits of integration on the interval and it does not have an infinite discontinuity on the designated interval. Okay, what if there's a case wherein it does? So in this topic, we extend the concept of the definite integral to cases wherein the interval is not finite, like 1 to 2 or 2 to 10. Let's say 1 to infinity or 0 to infinity. Or let's say negative infinity to 25 or negative infinity to infinity. So that is the interval is infinite. The second type is when the function has an infinite discontinuity. So meaning the function, when plotted on the interval a to b, may utol. So na-discontinuous siya. May infinite discontinuity siya. So this is where improper integrals come in. Okay? So we divide it into two types. So type 1 is that improper integral wherein the limit or limits of your integration is infinite. So this is an example. And the second type is when your integral itself is that scenario wherein the integral or the function itself has an infinite discontinuity on the designated interval or limit. If you notice class, the limits here are not infinite. Wala man disang infinity sa atong limits. But this function is having an infinite discontinuity within this range of negative 1 to 1. What does this mean? If I will answer this integral and substitute negative 1 to 1 to this function, it will have an infinite discontinuity. You will know that when we go to there. It's not that the limit is infinity, but the function has an infinite discontinuity on the designated interval. Okay, so for now, we will focus on the first type, wherein one of the limits or both limits of integration is infinite. Okay, now I'll go here. Under type 1, we have three cases. It's either the upper limit, which is infinite. So you see here, from a to infinity. Now, this is comparable to saying that you're going to evaluate the limit of what? The integral of this function from a to t. Take note, we change the infinity to t as t approaches infinity. Again, I will repeat. You will evaluate this integral is evaluated not as an ordinary integral, but in this manner. You will evaluate it by taking the limit of the integral of the function from a to t as t approaches infinity. Now, you may ask, Miss Ali, can we have the letter t change to any letter that we want? Of course. If you want this to change, if you want this change to z, or y or v, you may do so as long as the limit here should be evaluated based on that variable that you use. If this is z, then you place here z approaches infinity. Why? Because the z that you have here replace the infinity in the original integral. Okay? Your original integral is infinity here. So you replace it with a variable and then evaluated that integral answer based on the limit of that, sorry, I admitted somebody, based on that variable approaching infinity. So this is case 1 or type 1. Another one is when you have negative infinity to b. So, Miss Ali, can we write here positive infinity to b? Of course not. Because when you speak class of infinity as positive, it is to be interpreted as a value that is infinitesimally large. Positive infinity is a value that is infinitesimally large. You cannot place it here because this is lower limit. So as such, you place your negative infinity, which represents a value that is infinitesimally small. Okay, small because it's lower limit. Its value should be lesser than the upper limit. Now, the manner of evaluating this one is exactly the same as this. Only that we change this time the lower limit to t. So notice, you evaluate the same function integral, but this time it's from t to b, your upper limit. And the limit is evaluated as t approaches negative infinity. See? So the same treatment as this one, only that this time it's the lower limit that approaches a value that is infinitesimally small. Okay, negative infinity. Now, what's the third type? This is the third type class. Both limits are infinite. So from negative infinity to positive infinity. This is where we apply the property of integral wherein for a particular interval, negative infinity, for example, to infinity, you can choose any value in between, and that value could be a, and you write the original integral as the sum of two. I keep on as the sum of two integrals comprising of these two functions, but this time the limit is negative infinity to a for the first term, and the second term would be a to infinity. Okay, we're using here the properties, one of the properties that we have discussed with the ordinary integral, and this is applicable to this case in here. So under type 1, we have three cases. It could be upper limit infinity, it could be lower limit negative infinity, or it could be both limits which are infinite. Okay? Now I will continue. Please raise concerns, questions if you have any. Now we go to this example. Actually, this is an example under case 1. The upper limit is infinite. So type 1, case 1. Now consider an infinite region S that lies below this curve here. So I'd like to project this one. That way you can see clearly. Oh, right. Excuse class, ha? Wala siya nag-move. I'd like to project so it will appear bigger. Just let me know if it's not projecting in your end. Okay? Now, you could see that your curve is one. This is your curve. This is your curve. Y equal to 1 minus x squared. Okay? And you are after the S region above the x-axis. This is our x-axis. The S region that is being referred to is in here because S is representing area or surface area. So that region is this S. Now, to the right of line x equal to 1. Now, where is this line x equal to 1? Now, from your analytic geometry, we know that line x equal to 1 is this. Ano siyang line, ang vertical line. This is your x equal to 1 line. So, you will determine the area under the curve 1 over x squared to the right of x equal to 1 above the x-axis. How will you determine that area? Actually, the area is this already. This is already the formula for that particular area. How did it came to this? So that's where we're going to apply the concept of the improper integral. So I will clear my markings if there are no questions. Are there questions? Okay, I will clear my marking. Then we go to the next. I will just escape, then we go here. So you might think, check again. You might think that since S is infinite in extent, because you say it's the area under the curve above the x-axis to the right of x equal to 1. When you say to the right of x equal to 1, actually that area extends here. Extends infinitely here. So you may say that, it says here, does it say? That since S is infinite in extent, its area must also be infinite. So manumdum ka nga, ati kay ang area nga ina to the right of x equal to 1 under the curve and above the x-axis, wala man nakatapusan, no? Kay sige-sige lang na siya. Ti ang area infinite man ako answer. Of course, it's not right. Why it's not right? Because you're going to apply the concept of how you will evaluate improper integral. So this is how you do it. Let me just put this down. Now, the area of the part of S that lies to the left of the line x equal to t, this one is shaded. This is the shaded part. So remember a while ago, we said that the area or the integral from, let's say, 1 to infinity or 0 to infinity is equal to the limit of that integral evaluated from 0 to t as t approaches infinity. So we will apply it here. You're not placing t here as infinite even though that's it. Amo magina siya, kay infinite ni siya. Wala ni di katapusan ang to the right x equal to 1. Why gina siya katapusan? You're not going to write infinity here, but you're going to evaluate it like this based on what we have discussed a few minutes ago. So you're going to evaluate this integral. The answer of this is negative 1 over x. And you will substitute the limits 1 to t. So first substitute the upper limit, which is t. So if you're going to substitute the upper limit t, you will substitute it only to the x. So your answer would be, I'll just change color. So your first answer would be, I'll place this negative here, negative. And then you will have 1 over t minus 1 over 1. You get it? Ang first mo gid nga i-substitute na limit, ang upper limit to x. So 1 over t minus ang lower limit, which is 1 over 1 for the x. You should never forget that negative there. That is why you have this, because this one becomes positive and that one is negative. So this is the area that you are seeing there. But it is not yet the answer because you haven't really determined the actual quantity. Remember that you have already limits here. If you have already limits, you're dealing with a definite integral, in this case, a definite improper integral, and your answer should be a specific quantity. It should not be like this. Then how do we finish off what we started? So this is it. I will just clear my markings. So how do you finish what you started there is this one, the limit. You see that the limit of a of t, meaning the area which is a function of t, is equal to the limit of your answer here of the integral 1 minus 1 over t as t approaches infinity. Notice now t is approaching infinity because in the original integral, this is infinity. This t here. You just change it to t, that way you can evaluate it. Because if you substitute the original values of infinity, class, you won't get a value that is real, okay, or something, a value that is definite. Okay, so your answer, if you substitute infinity to the t, would be 1 minus, you substitute infinity here. So that would be 1 minus 1 over infinity. 1 over infinity is 0. So the answer is 1. So if you're going to be asked what is the area under the curve, 1 over x squared to the right of x equal to 1, you don't answer infinity. The answer is 1. That's the essence, or that's the significance of what we're doing here. Although, upon looking at it, you will see infinity, kaya wala man nakatapusan dao. But actually, if you're going to apply the concept of the improper integral, the answer is 1. You change the infinity to any variable that you want and then evaluate the answer of your given integral based on the limit of that variable approaching infinity. Do you get it? You have any questions? Okay, so you're silent. I hope you get what I'm explaining here. I will just clear my markings. Okay, I like to end in this part here. So I'll end here. So the shaded area of the region approaches 1 as t approaches infinity. This is just an explanation of why you have this as 1. Why? Because, for example, if you assign t equal to 2, this area will be 1 minus 1 over t, which is 2. The answer is 1/2. If this t is 3, you will have 1 minus 1 over 3, and that would be 2/3. It's 1. If this a is 5, you will have 1 minus 1 over 5, and the answer is this one, 4/5. So the bigger the number of the t, because t extends infinitesimally to the right, because we say that the area should be to the right of the line x equal to 1. As we make the t very large, the value of the answer, this is 1/2, this is 2/3, this is 4/5. What happens to this value? This becomes nearer and nearer to 1. So the area approaches 1. So that is why the answer is 1. You don't answer infinity. Because if you make this 1 over 100, this would be even very near to 1. Why? Because the value that you are subtracting becomes very, very small. So you don't answer an area which is infinite, but you answer an area which is 1, because it approaches that value. So that's the graphical representation of this answer that we have here, using the evaluation of the limits to properly evaluate an improper integral. So in closing, so we say that the area of the infinite, so take note, infinite region S is equal to 1, and we write that the integral of 1 over x squared from 1 to infinity is the limit of the integral of 1 over x squared from 1 to t as t approaches infinity, which is equal to 1. This is the example of case 1 under type 1 of the improper integral. Do you get it, class? Do you have any questions? Okay, so this is under case 1A, or case 1 under type 1. So we will continue this next meeting. I'll stop sharing.